So, how should we approach this question? My first advice is to sketch the configuration and then decide what principles we can apply. Then we're told what result we need to derive, this proportionality between P minus P1 and V minus V1. So we don't need to get the constant proportionality it's suggesting. And then there are two amounts of work that we need to compute, and there are two, and we remember that work done by a fluid is equal to pressure times dV, or the integral of P dV. And also, so we can do that integral mathematically, or we can do it graphically, because the work done is the area under the pressure volume curve. So I suggest you pause the video now, try and sketch the problem, and see how far you can get with those hints I've given so far. Okay, so I'm just going to begin by sketching out this piston arrangement. So there's the piston, and we know that it's not moving initially, and it's at later times as well it's not moving. So we can apply the principle of static equilibrium. We have a force on the left-hand side applied by a spring, and we have a pressure inside the piston. We just call it P and volume V. Initially we have P1 of 1 bar and volume of 1 meter cubed. On the other side of the piston we have a pressure, atmospheric pressure acting, or 1 bar, so we just call that P1. So what do we know about the magnitude of the force? It's applied by a spring, so we assume that the force is proportional to displacement. So the force is equal to the spring constant times x, and x is the displacement of the piston here. So at the moment this isn't the initial position of the piston, it's some later time once the pressure and volume have increased. Okay, so now we've mentioned that we need to apply the principle of static equilibrium. That means to equate the forces on each side of the piston in order to solve the problem. So I suggest you have a go at doing that before we proceed. Okay, so we need to equate the forces on both sides of the piston. So on the left-hand side, the force will be pressure times area, P, A. And that's going to be balanced by the pressure on the other side of the piston, which in this case is still P1, the initial pressure, A, area of the piston, it's the same area. But there's an additional force, which is F, or Kx. Now, what the question asks us to compute involves the quantity P minus P1, and we can see that we have P and P1 here. So what we can do is say that P minus P1 is equal to Kx over A, or that P1 minus P1 is proportional to X. Similarly, we can say that the volume, or the increase in volume from its initial value, V minus V1, is proportional, or is equal to A times X. And so therefore both of these quantities are proportional to X, and we can say that P minus P1 is proportional to V minus V1, which is what we've been asked to do. Okay, so the next part of the question, there are two, we need to calculate the total work done. So part A, there are two ways to do this. Either we can integrate P dV, And we have, in order to do that, we need to know the actual relationship between pressure and volume and x, or we can do it graphically. And here, just to, I think it's more illustrative and a lot easier to do it graphically. So if we plot the PV diagram, maybe have a go at doing that yourself before I show you. But it will look like this. Here's this axis is P, V, initial V1, V2, P1, P2, this is the path that, the reversible path that that our state follows, or the thermodynamic state follows, and the work done is the area under this curve. So what we have are two parts of the curve. There's this area down here, which is a rectangle, and this area here, which is a triangle. And so the total work is the total area. But what do these two areas correspond to? Here we're working against a pressure of P1, a constant pressure. So we could say that this is the work done against atmospheric pressure, or the background pressure P1. Whereas this pressure, this increasing pressure with displacement, is due to the increasing force on the piston as the spring gets compressed. So the total work is equal to the work done against the spring plus the work against the atmosphere. And so the work against the spring is this triangle, and the area of a triangle is half times the base times the height. And the area of the rectangle is simply the base times the height. So now we'll put the numbers in, and we recall that the pressure changes from 1 to 2 meters cubed. So that's 1 meter cubed is a change in volume. Change in pressure goes from 1 till 5, so that's a change of 4 bar, and we need to multiply that, convert that into pascals to work in SI units. And there are 10 to the 5 pascals in 1 bar. And then we need to add on the work done against the atmosphere, which is change in volume is 1 meter cubed times P1, which is 1 bar or 10 to the 5 pascals. So this is the work done against the spring is 2 times 10 to the 5 pascals. And the work done against the atmosphere is 1 times 10 to the 5 pascals. And the units of the work done, units of work are joules. And we've been working in SI units, so we don't, it's not kilojoules or anything else. And then the final part of the question asks the work done by the spring and the total work done. So the total work done is going to be 3 times 10 to the 5 joules. And the work done against the spring is just the first part of this, which is 2 times 10 to the 5 joules, or we could convert that into kilojoules, which is 200 kilojoules. So just to recap, we could have done this algebraically by integrating p dv. That would be a lot more difficult. So sometimes it's just useful to draw things graphically, and then it makes sense and it's much easier.